Thanks for coming. This is lecture 21 out of a series of 12, something like that. We'll have to revise that announcement. Yeah, dyslexia. So today I've got three topics that involve sort of Matlab programming. They're kind of leftover additions to things we covered before. So we'll get into some stuff on ICC color profiles. People want to know more about the internals of profiles and how color management works inside. We'll take a look at ray tracing in a particular simple example that's relevant to some of the digital cameras we have around here, and an example of some diffraction calculations that are also relevant to some of the things we do. So let's start with profiles. This will be at least half the lecture. We've heard from both Steve Johnson and Uwe Steinmuller about color management in various contexts and cameras and printing and so on. And so since it's a technology course, people want to know what's inside these things and how they work. So if you pull down the spec, which is it's a freely available standard, unlike most standards that you have to pay money for, this one was jointly developed between the International Color Consortium and some other standards organizations, and they're not in the business of charging money for their standards, so you can actually get this one and read it. You can read every version of it since about 1994. And it's a simple file format. It's got a header that's got a bunch of miscellaneous junk in it, and then it's got a sort of one level of simple self-describing tag structure. So there's a table of tag signatures that tell you where to get the tag data. So that's nice. That makes it easy to parse the file. And once you've pulled out a block of bytes called sig for the signature and data for the data, you can write a simple switch casement in Matlab, go through there and do something different for each different signature type. So this is just a piece of the code I'm showing here where we simply convert the data to character strings and print it out if it's something that looks sort of like a character string, and then we have a bunch of more specialized routines for parsing the data block if it's something interesting that we want to look at. So I had to kind of go through the specs and see how it's structured and write little bits of code. So you can whip out tables and XYZ data and strings and stuff this way. So I have this little routine called read ICC profile, and if you give it the more audience members, good. If you give it the sRGB profile, which is a standard profile for the sRGB color space as provided by Hewlett-Packard, it'll run through there and it'll print out the header. And first thing you notice in the header, well, there's a bunch of junk in there, but hold on. I underlined a little piece here, MNTR. That's a 4-byte block of numbers that says this is a monitor type profile, and they pick their numbers to be printable as ASCII as well, so you can read it. And then it's got other blocks of numbers in there. I lost my cursor again. Hold on. I gotta put this back in arrow mode. It keeps wanting to disappear on me. RGB here means it's a profile for an RGB color space. That is, the input data, the device data is in RGB space. The XYZ means that the profile connection space is XYZ, and I'll show you what that means in a bit. This is a little code that means it's an ICC profile. This is the primary device manufacturer, and this is, I forget. But if you go down through these tags, there's all kinds of stuff in there, like the copyright tag. It turns out there's a list of required tags in a profile, and copyright is one of them, which is kind of annoying because it means you can never give somebody a picture with an embedded profile without giving them a copy of some copyrighted piece of material. So why they required profiles to be copyrighted is sort of beyond me, but that's in there. So anytime you transfer a photograph, you're potentially doing a copyright violation. Isn't that sweet? And you can't leave it out. You could put something in there that's not a copyright notice, of course. If you create your own color space in Adobe Photoshop, which is easy enough to do, you can create your own custom profile for your own RGB color space, and it'll have Adobe's copyright in it. There's a description tag here, and what you see in a lot of these tags is what looks like the same text printed out twice. And it's really because the structure of that tag type allows you to have both an ASCII string and a Unicode string in there. And the Unicode prints out a lot like ASCII when you ignore the nulls in there. So if you go on through that profile, some of the tags you pick up in there, there's a measurement tag that says that the stuff you want to measure according to this profile will be illuminated with a D65 illuminant. It's got some codes in there that specify the measurement geometry and stuff like that. But since it's really a monitor profile, it's not obvious what that stuff is good for. There's a white point tag that specifies the white point of that of the sRGB color space in terms of XYZ coordinates. So you can pick up those numbers and divide them by the sum of x plus y plus z to get the little x, little y chromaticity coordinates and throw them up on a plot, and that's what I've done here. And it's kind of hard to read where it says white point here because there's a black point and an illuminant that plotted into the same location, so the text just stomped over each other. But again, this is just an illustration of how you can use trivial code to see what's inside of a profile. It's got also the XYZ coordinates of the 3 different primary colors. So the red primary here maps to this XY coordinate and so on. Same with green and blue, so you can see what the color triangle looks like. And I've plotted on here the locus in this space of the pure spectral colors, which is easy to get from you pull down the XYZ standard observer curves from somewhere and just plot it. There's other tags in there like the device manufacturer tag and device model tag, which don't really apply very well to a standard RGB color space designed for monitors, so they stuck into those tags the International Electrotechnical Consortium, or whatever it's called, the standards body that defined this profile. They put their info in there in case you want to look them up. There's a viewing description tag that, again, it references some viewing conditions that you can look up. And so, it says when you're looking at your sRGB monitor, it tells you how bright the room lights should be and stuff like that in order to see the right colors. And the other thing that's in there, besides the XYZ descriptions of the chromaticities, are the curves that define the nonlinear encoding of primary intensity into numbers in the file. And actually, it goes the other way. So this is an expansive curve, which means it's indexed here by essentially the numbers in the file. They always use ranges from 0 to 1, but then they map them into the min and max numbers in the file. So this really corresponds to 0 to 255. And then on the ordinate is the intensity at which you're supposed to reproduce that primary on your monitor. And this is not exactly a power law curve. We've discussed this sRGB funny curve before. If it is exactly a power law curve, then the TRC curve, that's a tone reproduction curve, can be specified as a curve having a single point, and if there's a single point there, then it interprets that as a gamma number instead of as a curve. So there's all these kind of options where the data format has one simple format, but the interpretation of that format has a few things going on. In this case, it's just, is it 1 point or is it more than 1 point? So the sRGB space has the same curve for all 3 colors, and these other numbers that I've printed out here, toe slope, top slope, and top gamma, are things that I calculated from this curve. I just looked at the slope of the curve at the 2 ends and characterized it in such a way that you could say approximately what gamma is in there. So in general, if you run this profile reader over a profile that has some such curve in there that's not sRGB, it'll give you an estimate of what the corresponding gamma is for that color space. What's in the header of the profile is all kinds of junk, and this is where things get a little bit nasty. And I didn't actually write code to parse all this because I don't need all these random bits of information, and you have to go study the spec to do it, and it wasn't worth the trouble. But it's good to have an idea what's in there. So, for example, I showed you that little string MNTR. That's the profile device class. That means it's a monitor class profile. Now, you may wonder why a sRGB profile that's used in typically embedded into the images you get out of all digital cameras is a monitor class profile as opposed to a camera class profile. Well, first of all, there is no camera class defined. There's no such animal. But more importantly, I think this gets at a issue that Steve Johnson brought up, on which I had a slight disagreement with him, where he said that the specification of sRGB as the color space in the images coming out of a camera was essentially meaningless and fraudulent. And I disagree. It has a very clear meaning. It says that if you display this image on an sRGB monitor, you'll get the colors that the camera manufacturer intended you to get. That's what it means, and that's all it means. And it's not fraudulent. It just says, you know, if you display this on an sRGB monitor, you'll see the colors the same way we intended you to see them. It doesn't tell you anything about how that camera interprets the colors in the scene, what it used as the scene white point, or what it used as its rendering strategy. It just doesn't tell you any of that stuff. It only tells you, view this image on an sRGB monitor. That's really all it's for. The notion of a profile connection space, I showed you that the profile connection space for this sRGB profile was the XYZ space, and there's only two options available here in the color management profiles, which are RGB space or lab space, and there's a essentially one-to-one relationship between those, except at black where it's many to one. So it doesn't really matter which one you use, except it affects perhaps the structure of your mapping tables in the case where you use table-based mapping. There's a thing in there called a rendering intent that's interesting. When you do conversions between different color spaces, you can convert with different rendering intents, and they have by default, or the one that you're supposed to normally use is called perceptual rendering intent, which means keep the colors looking right, whatever that means. And it's not all that well defined, although in more recent versions of the standard, they've tried to define it better. And there's things in there like the XYZ coordinate of the illuminant or white point of the profile connection space. And you can put the coordinates of D50 color in there as the white point of your profile connection space. And in fact, you have to put those numbers in there. And if you put any other numbers in there, it's not a valid profile. So there's a place you could specify a different white point, but it's defined that no other white point is allowed. So it's expansion room. So here's another kind of profile. This is a scanner profile. This one I found laying around on the web somewhere, called EPSN1P04.ICM. So that's an Epson scanner profile. And if you run it through the same program, prints out the header, it starts off with KCMS. That's the Kodak color management system, which was one of the earlier color management systems that was out there and working. This is copyright 1992 to 94. So you can see this one is 15 years old. And if you go through it, the code that I have, it has this big switch statement that has an otherwise in there, and it says, you know, if you didn't recognize what the tag signature was, print it out and say it's unknown. So it prints out a bunch of these tags whose signature starts with a K, and I thought, that must be a Kodak signature. And I read the spec and found this line that says, private data tags allow CMM developers to add proprietary value to their profiles. And as you can imagine, that creates all kinds of problems, because if you've created some kind of proprietary value for your profile, and the only compatibility hack is that other people reading that profile ignore tags that they don't recognize, then you're going to lose some stuff. And it's not clear what all is in there. There's a bunch of strings. It's pretty clear from this one that the scanner for this profile has been calibrated for measuring Ectacolor Plus. I think that's a color print paper. So when you put color prints on a scanner and you want to reproduce the color of that print, it helps to know what the media is that you're putting on there. If it's a certain color print paper with a certain set of colorants in it, then the scanner will respond to that in a certain way. And this is particularly important for scanners, because they generally do not attempt to be colorimetric devices. They're really densitometric devices. That is, they have either 3 sets of filters or 3 illuminants, like color LEDs or something, that are designed to measure the densities of the cyan, magenta, and yellow dyes in the print that you're scanning. And those can be tuned up to work well for photos or for printed ink type pages. you can optimize for one or the other or make it work pretty well for both, though you might need slightly different profiles for the things. If you put some real color objects on there, like you put your face down on the scanner and the colorants in your skin are made out of oxygenated hemoglobin instead of magenta ink, you're going to get different kind of responses, and the colors are not going to be right. But that's not what those scanners are designed for, and it's not what they're profiled for. But it kind of illustrates one of the issues in why Dan's laughing. He's thinking, I wouldn't put my face on that scanner. You don't know what other body parts have been on there. You know? Yeah. So with a camera, you have kind of the same issue, although they try to design cameras to be more like colorimetric devices, so they can shoot all kinds of different materials and get the relative colors about right. So you try to get the observer metamerism of the color to be as low as you can, whereas with a scanner, that's usually not an issue because you're usually scanning stuff where you have a pretty good idea what the colorants are. And you can make a profile for different kinds of colorants if you want to. So what's in this scanner profile is a lookup table thing. Yeah, Martin?
Could you give an interpretation of what a scanner profile means to get a very clear one from the monitor profile?
Yeah, so the question is, what does a scanner profile really mean? And that's what I'm kind of getting into here. So what's in this profile next is this thing called a lookup table. And if you read the section in the spec about that, you find this tag called a A to B0 tag. You say, well, what's that? And there's three different, when you find the tag signature and you go get the tag data, you get this block of data, you still don't know what type tag it is. You have to actually read the tag and read more of the spec to figure out how you tell what it is you got. So there's like three different types here. There's this LUT8 type, a LUT16 type, and a LUT-A to B type. And what they're in there for is to map the colors of the device to the profile connection space. So the device in this case is a scanner, and it measures these three color densities of some sort and reports them in some way. Maybe it has already done its own best estimate of a conversion to an RGB color space so that if you display it on your monitor, it'll look about right. But what you want your profile to do then is to take that point in 3 space that the scanner thinks of as representing an RGB color, and you want to know really more exactly what color that is. And the way the color profile does that is it maps that point in 3 space to a point in a known standardized space, namely the profile connection space. So this is a color transformation from device to PCS. And then let's see. So what's a PCS? So the profile, as I just said, tells you how to get colors to or from between a PCS and a device in one direction or the other. The PCS is usually a space that's represented using 16-bit fixed point fractions, linear CIE colorimetry XYZ space with a D50 white point, or optionally it can be, sorry, that should say D65 white point, which is what most monitors use. So that brings up a problem right there, that the monitor colors don't use the same white point as the profile connection space, but that's a separate issue. The PCS can also be a lab space, that is L star, A star, B star, which is a transformation of XYZ. That transformation itself depends on what white point you use. So once you've specified the white point, that becomes 1-to-1, but with a nonlinearity in it. And because of that nonlinearity, you can actually get away in most cases with 8-bit precision instead of 16-bit precision. And one of the reasons they gave this kind of flexibility, instead of standardizing on a particular profile connection space, they gave this kind of flexibility in order to allow the tables to be smaller, so you could use 8-bit data instead of 16-bit data. That was important back in the early 90s. When you were embedding profiles and images, you didn't want, if you could cut the amount of data in half on your tables, you wanted to do that. Nowadays, memory and disk being about 1,000 times cheaper, that doesn't matter as much, but there's all these options in there that have to be dealt with. So this profile connection space has a lot of details hanging on it too, like the measurement geometry of the whole color management system is centered around viewing prints under a D50 actual illuminant. And you want things on your monitor to look like they're going to print, and you want things from your scanner to take prints like that and reproduce the right numbers so that if you print them again, you get the same colors back. So those prints have to be measured, and they get measured with a certain color light and a certain lighting geometry, and that's all specified as part of the profile connection space. So I mentioned a couple of classes of profiles. We looked at the scanner class and the monitor class. There's also a printer class. There's a device link, a color space conversion, an abstract, and a named color profile, most of which you don't need to be too concerned about. But again, there's no camera class of profile. Cameras, when they do get profiled, they use the the scanner type profile, which people often refer to as an input device profile, but is originally conceived as a scanner profile, and it's really doesn't really do great service for cameras. And the trouble with cameras is that the whole response of the camera depends too much on what the lighting is, and you really need sort of a custom profile for every lighting situation, and it may also depend on a lot of other things going on in the camera, like some subtle sensor nonlinearities. Your sensor may behave slightly differently for short exposures than for long exposures and stuff like that. So generally, instead of characterizing a camera with a profile, the manufacturer characterizes it in much more detail than you could even get in a profile over a broad range of conditions, and they put all that calibration information into the camera, and they use it to convert their images into something like this sRGB space, or something that represents their best job of mapping it into sort of known color space with some preferred rendering of the scene based on whatever the manufacturer's preference is. If you use a raw data type capture, that same transformation is represented in the manufacturer's code for later converting raw data into some kind of an image. People continue to want to put profiles on that, but the profile is kind of a blunt tool compared to what's already done. So I don't understand the attraction for wanting to profile cameras. So among the other things in the data header, there's a bunch of signatures for different color spaces. So right up in the header, you can choose XYZ or LAB space as your profile connection space for the profile. And you can also choose the color spaces that this profile applies to. So both the scanner and the sRGB space we looked at were RGB device spaces. One of them was XYZ profile connection space, and that was the sRGB, and then the scanner used the LAB profile connection space. So let's go back and look at what was in that scanner thing. Yeah.
So when you change from sunny to cloudy to flash, you're changing the profile.
Yeah, when you change your camera or your raw converter from sunny to flash to
For the camera itself.
yeah, on the camera or the conversion, you can think of that as changing a profile, but the calibration data for those situations is generally not represented as a profile, but it's usually done in a more proprietary way because there's more stuff you can calibrate about the camera and the sensor than just the illuminant. One place you can look for how that's done is in the open specification for Adobe's digital negative format, DNG. We'll be hearing a lecture on that actually in 2 weeks, I think, on raw files, so we'll hear more about that. But they basically represent, in the DNG file, they represent the camera's profile for 2 different illuminants, and then they give you the option to interpolate and extrapolate between those. So you still have the flexibility of changing the illuminant using a profile for sunlight and a profile for tungsten light as sort of reference points. You can pick anything in between or even beyond that range. So if you just pull this data block out of this scanner profile, this A to B block, you want to know this is a thing that was described as mapping device colors to profile connection space colors, and you can just plot it and see what's there. You can learn a lot by just making plots of things and see what's there. So here we interpret it as 16-bit shorts, make a plot, and you can see there's obviously 3 what look like lookup tables here. If you look closely, you can see 3 lookup tables there, and you get this big mess in the middle that's got some nearly periodic structure in it. So you say, okay, you get some idea what's going on in there, some kind of tables. You can go look at the spec some more and figure out what's what. And it turns out what we're looking at there is this thing, there's all these different things that can be in there. We're looking at this thing that looks like a clut B, which means there's a set of input nonlinear tables A, there's this multidimensional color lookup table, and then there's this set of output curves B. And there's other things that could be in there, and so you have to read about how to parse it all out and so on. And when you pull it out, you can plot those things separately. So what the scanner profile is doing is it's taking the numbers out of the scanner and it's running them through this compressive nonlinearity. It's sort of like a gamma curve. So you put a lot of gain near black and less gain near bright colors. I don't know if that's because the numbers out of that scanner were not already gamma compressed, or maybe they were already gamma compressed, but we wanted to compress them more, so it's more like a cube root compression like you'd use in a lab space. But anyway, then they get mapped through this this is a 3-dimensional LUT. There's 3 tables here. Each one is indexed by the 3 colors from the 3 input channels. There are 16 points or 15 steps spread across the range. So you interpolate within those. So you take the 3D color, you compress each component through this, you look up and interpolate through this, and then you take what comes out of that and you run it through this set of curves here. And that gets you to the profile connection space, which in this case is LAB space. And you can see these curves. There's a identity curve here for the first dimension, and that would be the L. And then there are these steeper curves for the A and the B. So they, for whatever reason, they didn't put that extra A and B gain into their multidimensional LUT. They put it into this table that follows it. And there's, because of all the power and flexibility in the ways you can factor this problem into curves and tables and so on, there's a lot of room for people who create profiles, to do a good job or a bad job, or make them easier or harder to deal with. And I'm not showing you the 3D structure of this thing here, but that's the next thing you could do, is you could kind of plot these things and see what they look like. Yeah, Jim?
Is it a linear lookup in the 16-cube space, or is it a higher order to avoid banding effects of discontinuities between?
Is the interpolation linear or higher order? I don't actually know. I think it's linear, but I'd have to go back and read the spec and verify that. With 16 steps and reasonable nonlinearities going into it, you probably won't see any Mach-bound effects from doing linear interpolation there. But this is the kind of thing that, again, Steve was complaining about, that profiles take this kind of a lookup approach that he thought was kind of coarse. And it can be kind of coarse, especially at the bottom end where you approach black and you need the most fine curvy adjustments and so on. The table can be a kind of a blunt instrument there.
I guess the real question is, in that multidimensional space, are the straight lines basically remain straight as you interpolate through the space? Is it just minor
Oh, yeah.
to straight lines?
Do straight lines remain straight? Well, obviously they're going to have little kinks when you cross the boundaries. And
As opposed to
yeah. I think they're minor enough that you probably won't see them. People are generally reasonably happy with the way the internals of color management works, I think. I mean, I haven't seen anyone point out that this is a problem or a limitation. I think if it is a problem or a limitation, you solve it by putting a better nonlinearity before you go into the table. So there's a whole bunch of optional things you can do and optional extras in the profile, and this table illustrates one space of those. So you got all these different profile classes on the left. The one they're calling input profile class is what I called the scanner. Display is what I called monitor, and output is what I called printer, because the 4 letters codes look like scanner, monitor, and printer to me. So, this A to B0 tag is generally required, or you either use the matrix and tone reproduction curve approach in the center column here, or you use this nonlinear lookup approach. And if you use the nonlinear lookup approach, the requirement is to use the perceptual rendering intent. That's what A to B0 means, and then A to B1 means a colorimetric rendering intent, and A to B2 means a saturation rendering intent. And those are all just sort of tweaks on how you want to map your colors, and that's, again, an area where you get into a lot of complexity and interpretation, both user confusion about what those are good for, as well as color management implementer confusion about exactly what strategy you should take in each of these optional situations. The spec, at least in the later revs, does have more information on order of preference for these things if multiple things are present and so on. You can have in the input profile these things on the right, the B to A type tags map the other direction from the profile connection space to the device space. And those would obviously be most useful on the output side, but you can have them on the input profile. And I think part of the reason there is to make it easier to go both directions, because if you've got an image in, say, sRGB space and you want to convert it back to an image in the scanner space, you can do a profile conversion. You have to be able to convert from an image with an output type profile to an image with a monitor type profile, which means all these tables need to be able to be run backwards. So if you've already got the table designed in there to run it backwards, it's a lot easier than if you have to try to run lookup tables backwards, which may actually not even be a one-to-one thing. Anyway, so it gets complicated. That's just to illustrate that. But what's actually in the profiles is usually not so much of this stuff, and it's pretty easy to look at, see what's there. So that's all I'm going to say on color management. I want to get into two more short topics, shorter. This is an example, just an image I pulled off the web to illustrate the notion of optical spot diagrams with ray tracing. Ram told us all about ray tracing in the stigmatic condition, that is where you know that all the rays from a given point on an object converge to a given point in the image. There's a lot of simplifying tricks you can use to map out how that optical system behaves and get its magnification, focal lengths, and all that. But there's another whole class of stuff people do with ray tracing, which is much more numerical, and that's to work out the behavior of systems that are not perfectly stigmatic and see what their aberrations are. So this is just a plot where the different colors scattered around here represent different wavelengths. It looks to me like I don't even know what I found here, but it looks to me like from the numbers that this is an infrared system, because they all look like long wavelengths, either that or they're in some funny units. And you can see that in the center, things tend to be kind of compact and circular, and as you get out to the corners of the field, you get these funny shapes called coma, because they're shaped like a comet. And the different colors don't all converge in the same place, and so on. There's all kinds of info on here. This is plotted out by a program. I'm not sure which program it is. It might be ZMAX or one of those commercial programs. It says reference chief ray. That means that the center of each of these boxes centered on the chief ray. The chief ray is the ray that would still come through your lens if you stopped the aperture down to a pinhole. So it's the ray that comes through the center of the entrance or exit pupil. And so that's just an idea of what you can do with ray tracing. But if you want to do your own ray tracing, you can work simple problems much more easily. So for example, here's a problem that comes up a lot in digital cameras. In film cameras, there's usually nothing between the lens and the film. And the lens manufacturers go to a lot of trouble with these programs to make lenses that converge all their rays very nearly perfectly onto the film and make very nice little spots. So if you take one of these very well-corrected lenses and you put it in a digital camera where between the sensor and the lens you've got a sheet of glass, like the cover slip of the CCD imager, or another sheet of glass with a filter on it to reject infrared light or something like that, or both of these pieces of glass that add up to 1 to 2 millimeters or something like that, you can ask the question, what does this flat piece of glass in there do to your image? And for a long time, people kind of ignored that and didn't see it as a problem, but it can be a problem. So you can just trace some rays numerically. You can just throw a bunch of rays as if they were going to perfectly converge at a focus, and then see what happens when you refract them through a flat sheet of glass. Yeah, Lance?
Might be worth mentioning that the frame of Phillips gigapixel camera, they found this plain old object to be a problem
Oh, yeah, yeah. Yeah, you mentioned the wrong name there, but yeah, the Gigapixel project guy, Graham something else, right? Mentioned that they were able to use a Plano optic in the middle of their optical system somewhere to correct an aberration that was otherwise very hard to get rid of, to allow them to simultaneously correct chromatic and other aberrations. So, yeah, the point is the same there, that an optical element, even if it's perfectly flat, can have interesting effects on the point spread. So let's just trace some rays and see what happens. So if we start with these magenta and cyan rays over here that are all converging toward this point in the focal plane, say we assume these rays come from somewhere far left there where there's a perfectly corrected optical system, big exit pupil, and they're all going to converge on a point, and that's the focal plane. Now we put a piece of glass starting right here. So this ray that comes in as cyan gets refracted to this green ray and comes over here. And it's a trivial piece of code to, at x equals 0, find the angle and compute the refracted angle and draw a line from there. And we just draw that line, make this picture. That's all it is. So it's a completely trivial piece of code. I'll show you the code. And what happens is that because of the refraction, the rays converge further back. So the first order thing is that the focal point moves back so that if it would have taken about 1 millimeter in air, it takes about 1.5 millimeters in glass, where that 1.5 millimeters, that 1.5 is the refractive index. We could have put another glass surface here and recomputed the refracted angle as it comes out of the glass and see where it goes. I didn't do that for this simple case. I'm just looking at the convergence of rays as if it's within a block of glass. And if you put a sheet of glass in there where these things converge, essentially what happens is they go in at some angle, they jog over, they come back out at that same angle again, and then it doesn't really matter if you put that glass further left or further right. It doesn't matter where you put it. So a given thickness of glass will have a given effect. If you zoom in on where those refracted rays are supposed to converge, the rays that are very close to the axis converge here, the paraxial focus. That's the point that was just moved back by a factor of refractive index from where the other focus was. But a lot of those rays miss that point. Those green rays are actually making a smallest bundle back here somewhere. So the focus moves further back for rays from the outer zones of the lens, and it's closer in for rays from the inner zones of the lens. And if you get off axis, that's what these other colors are. Let me go back. As the caption on this image says, we've got 2 different chief ray angles. And what this is supposed to really be simulating is 2 different positions in the focal plane. The chief ray comes from the same place in both cases and hits the focal plane in different places, but I've remapped the problem to where the rays are going to the same place. So they were all converging here. So these red rays correspond to the case where I take a 35 millimeter size sensor and I go 18 millimeters off center, which is the middle of the short edge of the 24 by 36 millimeter imaging area. And the angle is computed based on an assumed distance to the exit pupil of the lens. That is, where the pinhole would be if I stopped the lens all the way down will give me that chief ray angle. So it's 80 millimeters away and it's 18 millimeters off center, and so it's the arctangent of 18 over 80 is the angle that corresponds to the middle of that bundle of red rays. So when you plot those rays, they're really following exactly the same laws, the same code. They come in, they're all initially aimed at the same point. They have some angle of incidence. They get an angle of refraction. So there's a red ray and a green ray both going through the same place here, but the red rays continue to go further off angle. And as they get further and further off, that point where they cross the axis gets further and further back due to the aberrations of that flat plate. And the smallest spot you can get is way back here. So this And there's another spot here which is pretty compact. It's got a lot of rays, but it has this long tail. So you sort of anywhere between here and here, you get this kind of a compact spot by different measures, but it has this comet look, this long tail coming off of it. This is labeled in millimeters, so you can read right away here the thing has defocused itself due to this glass plate, not just by the 0.5 millimeter to account for the glass, but by another up to 80 microns, depending on how you focus it, at the outside of the field. So if the center of the field is focused here and the outside of the field is over here somewhere, that corresponds to a curvature of field. The spherical aberration corresponds to the fact that different zones of the lens focus in different places. So there's a region in here that's kind of variably sharp and fuzzy and so on. So you can see all these effects pretty clearly with this completely trivial piece of code. This is all the code right here. Top half is just sort of setting stuff up, and then there's this little loop here, and all the work is done in this line that says that the refracted angle is the arc sine of the angle divided by the index, and you just plot it. So the point is that you can make these, arbitrarily complex $100,000 ray tracing packages that you can pay for and do big problems on, or you can do this, one-off quick hack thing to make a plot and see where you can, get your results by making measurements off a plot. And that whole range of options is useful, I think, to be able to deal with. So here's a case. This figure is actually from I think this one was from the 1911 Britannica, so it's in the public domain. It's one that I found and stuck in the Wikipedia, so it's in there too. This illustrates what happens in the kind of higher dimensional situation. These lenses are really three-dimensional, and I just was, if you had just a cut through the middle where you're looking at these rays converging at a point here, and I showed that, at some other image height, how it converged differently, and I had the plate in here and so on. But there's this other dimension in and out of the board here, and things in that dimension, they can converge at different distances, so you get astigmatism. So if you really want to work these effects in 3 dimensions, the code's going to be a little more complicated. Instead of just having x's and y's and angles, you're going to have 3-space representations of your ray positions and direction vectors and surface normals and so on. And of course, all you guys that have done graphic ray tracing and so on, that'd be a piece of cake. But if you want to do it for optics, probably better off just buying the tool and doing it right. Yeah.
I feel like the discussion of optics is class. Because a lot of information about kind of class and optical development, you're basically feeding digital sensors in a lot of applications. And it seems as if fiber optic elements can do wonders. And maybe they're underexploited.
Yeah, so the question is about how with digital there's maybe new opportunities to use unusual optical elements like fiber optic bundles and so on, right? Or fiber, you talking about bundles or some other ways of using fibers?
I was thinking particularly about making an optical element which isn't constrained to have a planar focal plane.
Right. Things with non-planar focal planes, and then you use an optical faceplate to bring that down to a flat sensor. Yeah. So there are a lot of technologies that use fiber optic bundles as faceplates to collimate light and move it from place to place. And you can make bundles into tapers, so you can take a big image plane down to a small image plane and things like that. There's all kinds of cool things you can do. They tend to all be relatively expensive because making those fiber bundles reasonably precise is quite an art. I have a friend over at Collimated Holes Incorporated that does that kind of work for a business, and they make all kinds of really wonderful stuff. Okay, so that's enough on geometric optics. So the final short topic is on simulating diffraction. Now, again, you can use the theoretical approaches with lots of integrals and get a lot of insight into the behavior that way. But you can also use numerical approaches to get some quick insights. And sometimes some of the problems you solve this way can be easier or have easier solutions. So if you just sum a bunch of spherical radiating waves from some set of source points that could be in an aperture or something like that, and you sum them in all the locations you care about, as complex waves and then take the absolute value, you'll get the light intensities. And those places you care about don't have to be in the focal plane, which I'll illustrate in a second here. So for example, you can do the pattern of diffraction from a single slit here. I made a slit that's 4 wavelengths wide, and I put some number of sources in here, and then for each point out here, I add up the waves from each of those sources, which is just, it's got a phase delay and it's got some amplitude that falls off with distance, and you just add them up. And then you take, say, the real part, and you can plot it here, or you could take the absolute value if you want to just see the intensity. This one shows the phase by taking the real part, and so you can see how there's a phase reversal at these nulls and things like that. So this is not an imaging system because it's not coming to a focus, but it illustrates a few things. When I first did this, and I got these ripples across the slit, I thought, oh, that's messed up. I need more points. So I threw more points in there. No matter how many points I threw in there, it had this nice stable ripple pattern. And I finally realized, oh, that's probably the actual diffraction pattern of that slit. And that's one that you don't normally read about because they usually talk about the far field diffraction, where you have this sync function pattern of distance out here. If you take the magnitude instead of showing the phase of that thing, it looks like this. And if this is correct, and I have no reason to think it's not, then that means that behind the slit you actually have sort of a concentration of light in the middle before it starts to spread out, and you have this kind of interference pattern of the waves across the edges of that 4 wavelength wide slit. And I thought, okay, that's a view of diffraction I hadn't seen before, and as far as I know, it's probably correct because it comes from simple numerical approaches. What I haven't done is to model what's going on the other side here, and this could be complicated by the fact that I just sort of assume there's plane waves that stop at this boundary, and in fact they'd have to either reflect or be absorbed or something, and so it may get more complicated to actually try to incorporate the physics of what's going on that's not in the slit. So let's consider a lens. So like we did in the ray tracing, if we assume a perfect lens, that is all the rays are coming to a point, in the wave or diffraction space, that means all of the sources are phased such that when you get to that point, they're all in the same phase and they'll all add up constructively. So you can take an array of points across a circular aperture and put them all in the right phase so that they'll have the same phase at some point. Or to simplify that, you can actually take a spherical cap and distribute everything in the same phase across that spherical cap because those points are all equally distant from the center of that sphere. So your focal point will have everything in the right phase, and I did that just because the code was easier. And then when you just add up these waves, complex waves, and then take the magnitude, you can see what the spot looks like. And there it is. So the focal plane is here where it's most concentrated. And this is the focal plane running vertically here. And you can see the nulls. The nulls are spaced at, they kind of look like wavelengths here, but these are not wavelengths. These are the nulls of the airy disk in the focal plane that are actually spaced at n times the wavelength, where n is the f number. But you can, and so that's pretty classical to cut it that way and see what that looks like. It's an airy disk in the focal plane. But what I was doing this for was to see what happens when you defocus it. And the thing that I never knew before is that if you defocus it enough, you get to a point where you get a black spot in the center. So I'll brighten it up some. Your optical spot, if you defocus it that much, will turn into a donut with a dark hole in the middle surrounded by a bunch of bright stuff. And it's generally kind of complicated to analyze this defocusing of a diffraction limited spot. There's a classic paper on it that I have on the SPIE reprint book on MTF analysis from the 50s, and a couple of papers on it where they plot it and analyze it and so on. It's kind of complicated, but I wanted to see what it looked like. So again, trivial piece of code lets you do these kind of explorations in wave optics, ray optics, and so on. And you may learn some things you didn't know before, like the spot size. It's not like you just took the diffraction limited spot and convolved it with a disk, which is convolving what a disk is what you normally think of happening when you defocus. And it's what would happen if everything was correct from the model of ray optics, that a point turns into a disk, and so any image, when it's defocused, you just convolve it with a disk. But because of the coherent nature of light and the wave effects, the effect of defocusing a diffraction-limited spot is quite a bit different from taking the diffraction-limited spot and convolving it with a disk. So this lets you have a good look at what that is. And the depth of field on this thing, if you write it in terms of how much the MTF is reduced or something, is probably from about here to about here. So if that's between the first nulls here is 2.44 times the F number times the wavelength, then maybe it's like, 5 or 10 times that much in the depth of field. So it's only a dozen wavelengths or so that are in focus here for this relatively low F number system that I've simulated. But you can do that for any F number, and the whole thing just kind of stretches out for higher F numbers. Yeah.
So people talk about good bokeh, is that how you pronounce it?
Yeah, good bokeh. Yeah, or however they say it.
And a lens, and I've seen mirror lenses with these little donut defocus areas. So is that the same thing?
The mirror lens gets its donut from the geometric ray optics, because in the mirror lens you've got this primary mirror, and the center of it is blocked either by a secondary mirror and or a hole in the main mirror. So when you defocus, you can think of that as being an image of the main mirror, which is a donut. Now, if you combine that with a diffraction-limited wave aspect, you could do that simulation here just by blanking out the sources in the center of that circle that I simulated. Simulate that coherent addition of waves from a donut of sources, and you could see what the actual bokeh is that takes into account both the geometric and wave effects of that mirror lens. That'd be an interesting problem. Yeah, other question? Sort of like a two-slit diffraction. Maybe it is sort of, because you got these two regions that interfere with each other, so you probably get some extra big fringing from that. Yeah. Okay. Any other questions? Well, thanks for coming.